This next very exciting lesson involves finding volumes of solids of revolution. And as a preliminary, we should look into how do you find the volume of a cylinder like this. And the way to do that is to find the area of the base and multiply it by the height. Of course, the area of a base is the area of a circle, which is pi times the radius squared. And so pi times the radius squared times the height gives us this formula for the volume of this cylinder. And if we hollowed out, cut a cylinder outside of a cylinder and call the inner radius small letter r and the outer radius capital R, you can see that we could take the large cylinder, pi r squared h, and subtract the small cylinder, pi small r squared h. So you should see that we could get this formula for the volume of our hollowed out cylinder. So again, the methods of discs and washers, we can set this whole thing up by using, you've heard this word before in the first lesson, the SAALI process: subdivide, approximate, add, take to a limit, and identify an integral from a Riemann sum that we will be having. And so let's see, here is our problem. Imagine that we have a function like this one, and we rotate that, that's what these arrows mean, rotate that entirely 360 degrees around the x-axis. And that's what we're going to find. We're going to find the volume of this solid right here. Okay, and how are we going to do that? Well, we can imagine subdividing this region. Okay, as you can see, I drew in a lot of these black circles, and that shows that the region is now subdivided. I didn't draw as many of them as I could have, but I think you get the idea. And we're going to pick one of these, maybe one about in here somewhere, and then look into, well, let's approximate this solid figure with a disk. Well, the disk is really nothing more than a fancy cylinder. That's fancy one of these turned on its side, of course. So we subdivide it and say, well, how would we find the approximate volume of that disk at the point c sub k when the interval it's across, from here to here, is delta x sub k. That's, remember, we've subdivided this. We put in a whole lot of these things. And the height of this cylinder is, or the radius, I guess, really is a proper word, would be the value of this length right here, which is f of c sub k, where c sub k is some x value in the interval delta x sub k. Or from, if you want to call it x, from x sub k minus 1 to x sub k. And so this height is f of ck, and that height is indeed the radius of this disk. The thickness of the disk, the height of the disk, is this. So now we can approximate that particular piece by saying, I don't think I did that anywhere. I meant to do that. This disk is has volume equal to pi times f of c sub k squared. Do you see why it's squared? Pi times the radius squared times the height. The height is times delta x sub k. And so that I'm approximating, I should have said not equals here, I should have said approximate the equal to, so bear with me a second. Now I think I'm saying it better. Volume is approximately equal to pi times the radius of the disk squared times the height of the disk, the thickness of the disk if you want. And yes, I know it's not really a cylinder because it's crooked here on this edge, but we're approximating it with a cylinder, and you can probably guess where we're going to go. we're going to say the volume of the whole figure is adding up all those disks. Well, that's easy enough to see. So add this disk and this disk and this disk and this disk and all these little disks. Actually a whole lot more than what I've drawn in there, but hey, give me a break on the drawing. I did pretty well with just drawing in 1, 2, 3, 4. I guess that's 1, 2, 3, 4, 5 disks I put in that one. But remember, we're going to put in an infinite number of those disks because we're going to say the maximum of the delta x of i's goes to 0. By the way, I note that by a flub I made here, I just used I as my subscripting variable instead of k. I hope that's all right with everyone, but it doesn't matter. Call it anything you want. So the volume is going to be equal to the limit of that as the maximum of those delta xi as the heights of those cylinders approaches 0. And notice that since pi is a constant, you can factor that out of the summation. And I did that right here. And that's the limit. And then if you looked at this particular limit, you should see, oh golly, isn't there an integral in there? And the answer is, yeah, that's just a Riemannian sum. A little interesting Riemannian sum in that there's a numerical factor of pi multiplier of that sum, but the integral from a to b, where a and b are the limits that were imposed upon the function itself. I didn't draw them in here, but a would be here, b would be about here. So of f of x squared, that's the radius squared, times dx. The dx represents the little thickness of this delta xi as it approaches 0. So there's our formula for the volume of our figure using the method of disks. If you want to say short cylinders, that would be the same thing.